today the focus will be recursion. Okay, let me start from the very beginning. So it's really important to see what a big picture is. There are many possible questions you might be given in the lab, the test, or the exam. So what I really want you to grasp in the lecture is the principle and see what will be the pattern of solution for any recursive problem you're given. Okay, I think that's the main goal we want to achieve in the lecture. Anyway, let's try. What I presented to you last time on Monday was this diagram here. Okay, let me just try to help you a little bit more. Just brush up. Let's go over some slides and then we'll go back to the diagram. Okay, again, so coding bat is really the nice source for you to try many exercises to get a feeling about recursion. Okay, what's the principle for recursion? Recursion basically saying you're trying to solve a problem by applying the solution multiple times somehow. But how exactly? You got to follow certain principles. So there are so-called base cases. So for those of you who might recall the concept about mathematical induction in math, you may want to review that part just briefly, okay? You can see quite many connections from mathematical induction to recursion. So they are both mathematically based, okay? But I wouldn't bother you too much about induction until later we have to prove correctness of recursion. Okay, anyway, for every recursive solution or recursive method you want to write, make sure you always got base cases. Base cases are basically small problems that can be solved immediately. So if you look at the diagram over here, so these are small problems that can be solved immediately. Okay, that's basically what I mentioned. And then, what about recursive cases? For recursive cases, that somehow you're assuming that you have some strictly smaller problems that you can solve right away. You cannot solve right away. However, somebody else solved that for you. You can assume they exist. You don't have to solve it by yourself. Okay? For recursive cases, large problem instances are not immediately solvable. So what we do is solve by reusing the solution. And now, what I underline over here, strictly smaller. Okay? Strictly smaller is really important. If you simply try to solve the same problem twice, you're going to run into trouble. Okay? But I'll illustrate to you what I mean. Okay? And then, over here, if you are given a big problem over here, what you have to do is to conceptually break it down into strictly smaller problem. You can see this is strictly smaller, that is also strictly smaller, that's also strictly smaller. And then assume you have the solution to each one of them, just assume. And then somehow your final solution to the original big problem will just be to combine these things together. So you will see all this kind of pattern occurring for every problem that we're going to have. We're going to see many examples today, so we'll keep emphasizing this point. Okay? Specifically, programmatically, if you see a method inside its definition, you simply call the method itself. Then you have recursion. Okay? Okay, so what I mentioned briefly about mathematical induction, that's something I'll leave it to you. You can review it. If you got trouble of understanding mathematical induction, you can come to speak to me. That's not a problem. Okay. Okay, recursion can be easily solved programmatically in Java. Okay, that's what you see, but we'll see more examples. Okay, so now, there's one thing I want to mention very quickly. So it is really important for you to know how to trace recursion. So for the very first two simple examples, I'm going to trace in complete details with you. But later on, you may want to trace at a higher level, so you should know both. Okay, let's try. At a lower level, you should know something about a stack. Basically, we already introduced this idea when we talk about exceptions, right? When you have a caller calling another method, you're going to put something on the stack and then keep stacking up, right? We're going to see exactly that. But let me just review very quickly with you. So these are certain words you can read, but I'm just going to go over some wording with you very quickly, okay? We're going to see exactly these kind of things when we do the tracing. Basically, keyword is about activation. Think about if I'm trying to execute a particular method M, what I would do is, as soon as I start executing this method, I should push this method onto the stack. Let's say somewhere along the way, M is trying to call maybe another, just make a recursive call. M with some strictly smaller, different input, let's say. So what I should do, let me make purple. So this purple. So as soon as I try to execute this inner recursive call, I should push this onto the stack again. And when I am trying to execute the purple one, the red one over here is set to be suspended. Okay, let me just highlight the word for you. So it's about suspended. What you will see later when I trace the first two examples in complete details, I'll keep trying to add something to the stack when the method call first become activated. I'll pop them off when they become deactivated. You'll see lots of things like that, okay? Anyway, I just want to point this out to you. So stack, as you will learn more in 2011, is a very primitive data structure to trace things, okay? But let's learn from examples. Let's do the first one, okay? Let's see a little bit of slides. I want to really just train you how you can think recursively, okay? This is your definition for factorial, okay? Just a review, remind you very quickly. Over here, n factorial is defined to be two cases. Either when n is simply equal to 1, that will just be 0, okay? N factorial, 1 factorial is simply 0. Otherwise, if n is somehow larger than 1, so that means the problem is slightly more complicated than what I can handle at the moment. What I will do is I'll say n times n minus 1 times n minus 2 all the way to 1. This solution here is not recursive, okay? I will help you a little bit. For those of you who already know, that's okay. But for those of you who have not known the recursive solution, I'll help you a little bit. Let's think about what's the problem that's being solved before we look at the solution, okay? Help you a little bit. Think about the problem I'm having now is the following. Let's say, for example, I got 4 factorial. That's a problem. Somehow, the size of the problem is too big. I cannot solve it right away. Let's peek a little bit beforehand. The final solution should be 4 times 3 times 2 times 1, okay? You can see this guy over here is exactly the size of the problem that I'm trying to solve. And now, can you tell me what this guy is, the remaining part? If somehow 3 times 2 times 1 follow the same solution pattern for factorial, would you agree it's actually the solution to a strictly smaller problem? 3 factorial. Agree? Okay? So now, that's really important. So now you can see that 3 factorial. You can think about this is the solution to a strictly smaller. Again, I want to emphasize strictly is really important. Okay? Strictly smaller problem. Okay, so now you can see, basically you say that's a 4 times 3 factorial, okay? When problem is bigger than what you can handle right away. So now, can we make it more general? If I give you the problem to solve n factorial, so now you have to think about when the problem is small enough for me to handle. If n is equal to 1, well, that should be 0 right away. What if n is somehow larger than 1? What would that be, right? Basically, you can think about 4 here is n, and then this guy over here is n minus 1 factorial. Okay, I'll write it down here. N multiply n minus 1 factorial. That's a recursive definition over here. Okay, let me highlight to you again before I answer any questions. Even though this example is very simple, I do want you to really see the insight into this problem here. Think about this guy here. I'll try to highlight more carefully. Look at this n over here, okay? And also look at the n minus 1 over here, okay? So now you can think about this n is the size of the original problem. And this n minus 1 is the size of a strictly smaller problem. And remember, I said the last step from the notes. You should somehow combine the two things together, right? So now the way I combine is simply to say, whatever n it is, multiplied by this solution. And now, do I ever have to calculate n minus 1 factorial in my code? I don't have to. Somehow it will just work out magically. That's an intuitive part, I would say. Anyway, I'm just talking about at a conceptual level to tell you what's really problem, what's strictly smaller problem, and what's the solution to the strictly smaller problem, right? Just get it straight, and then we'll trace. Any question about this? Okay, let's now try to trace that a little bit. Okay, this trace will be quite straightforward, but I think it's still worth doing altogether. This is the recursive solution I just talked about translating it into Java will be quite straightforward. What we will do is we simply define a integer accessor called Factorial, takes integer n. And then we say that just have some integer result, eventually just return it. If it is simply equal to 0, and then the base case will be 1. Okay? Sorry, I said something wrong previously. Sorry about that. I meant the base case should be when n is 0, factorial should be 1. I read it the wrong way. Beg your pardon. Okay? When n is equal to 0, then that should be 1. It's larger than 0, that should be n multiply n minus 1 factorial. Okay? So now let's see how we can understand this code here. When n is equal to 0, and then we have the base case, which is result equal to 1. Otherwise, we have result is equal to n multiply factorial. You can see we are making a recursive call over here, calling the same method. And then this is important. n minus 1 is guaranteed to be smaller than n, guaranteed. Okay? The intuition is if we start with 8 factorial, eventually we will hit the base case for n equals 0, eventually, at some point. Okay? Now, let's trace it all together to get a little bit more insight. Okay, let me clear this, and then we'll do it together. And let's do something that may not be too big, okay, just to begin with. Let's say we want to do factorial of 3, okay? The first question you're going to ask yourself, when I execute factorial 3, am I going to reach the base case or recursive case? In this case, recursive case, right? Because n equals 0 is not true. It's not too big, okay? So what we will do is, oh, by the way, as soon as you try to execute this particular factorial method, you're going to activate this particular method. So you would say, I'll say fact, just for short. Factorial 3 is pushed onto the stack right away, okay? Eventually, once factorial 3 is calculated, you'll be popped off from the stack. Yeah. So now let's try this. And now we know that it's going to go for this particular line. So that what that will do is it's going to do 3 multiply factorial, I mean, use a different color. It's going to be, let's say green. Factorial of n minus 1, that'll be 2. Okay? 3 is very easy to calculate. But now we have the issue about factorial 2. We want to calculate it. So we're going to activate that, factorial 2. So now you can see we got 2 method calls on the stack. What does that mean? Currently, we're going to execute factorial 2. However, factorial 3 is not completed yet, just suspended. Okay? And then, when we want to do factorial 2, so that means we're going to execute this factorial for the second time. And then n is going to be replaced by 2. Okay? So now, are we going to reach the base case or recursive case? Recursive, right? As long as it's not 0. Okay? The idea is eventually we should reach 0. And then what we will do is we're going to execute this, and then we're going to have 2 multiplied by, so now there should be factorial 1. Okay? In order to calculate factorial 1, we have to activate it, factorial 1. Okay? You can kind of see the pattern. Let's see how we can reach the base case. So now, when we want to calculate factorial 1, we're going to execute this the third time, 1. Are we reaching the base case according to the method? Not yet. Okay. So now we're going to reach here again. So now we're going to have 1 multiply, final color, how about pink? Factorial 0. So that means we got factorial 0 here. You can see our very original problem was to calculate factorial 3. In order to do it, we have to somehow calculate factorial with different problem sizes, right? 4 times in total. Okay, and then, so now how do we calculate factorial 0? So now, 4th time, is, n is going to be 0. We are reaching the base case this time, for the 4th time. And then it's going to say result is equal to 1. And then we're simply going to return the result being 1. Okay, so that means what we will do is, you can think about this is going to return 1. And then we simply remove it from the stack. Okay? So now, if you think about the stack, after removing factorial 0, we should go to the top of the stack to execute. So now, what should be executed? Factorial 1, we should really continue with where we left off. Okay? So now what we will do is, so now we should really continue with factorial 1. Factorial 1, what we did was up to here. And because factorial 0 returns 1, so this guy here is going to be 1. 1 multiplied by 1 would be 1. So that means factorial 1 is going to be completed, and then it's going to return 1 multiplied by 1. So that will also be 1. Okay? After this, what should we activate now? Factorial 2, right? Just keep going, okay? And then what we will do is factorial 2, and then this is where we left off. Just follow the color. That's why I put the color differently. So now factorial 1 actually return 1 to us. So now this guy here is simply 1. So to calculate factorial 2 over here is going to be 2 times 1, which will be 2. So that means it's going to return 2. Okay, finally, the final thing to be activated is our original problem, which is factorial 3. Okay, let's do that quickly for completeness. So we're going to do this now. So now this is where we left off. So it's going to be 3 multiply factorial 2 returns 2. So this guy here is 2. 3 times 2, 6. So that means eventually we're going to return 6 from this factorial and then pop it off. So that means after the recursive call, the stack will just be empty. But on the way calculating the result, it will be stacked up for suspension. Okay, one more thing before I take your question. That's kind of the very low level tracing, but you should know. If you think about a little bit higher, like this, what we started with was factorial 3. In order to calculate it, we have to first calculate factorial 2. Haven't reached the base case yet. We're going to calculate factorial 1. We haven't reached the base case yet, so we're going to go for factorial 0. And now this is the base case, and it's going to return 1, right? And then as soon as we got 1 here, and now it's going to be 1 multiplied by factorial 0, which is 1. And this guy here is going to give us 1, right? And then this factorial 2 is going to be 2 multiplied by factorial 1. And we just got its result, which is 1. And this guy here is going to return 2. And we go back to the very original problem. Now this will be 3 multiplied by factorial 2. And we just got that one. So that's 2. So 3 times 2, which will be 6. That's a little bit higher level of tracing. That's what you should get comfortable with eventually. Okay? Guys, that's your first recursion. It's more like a hello world example. Right? Factorial usually is the first example people introduce. Any questions? Okay. Now let's do the second one. Second one is Fibonacci. All right. Let's first of all, let's go over a little bit slides. Okay. That's factorial. And then, before I talk about Fibonacci, I do want to talk about common errors. That's really important. Whenever you're trying to define your own recursive solution, you want to make sure at least 2 things should be present. You shouldn't really make that kind of mistake. Number 1, can you consider this particular alternative version for factorial? Yeah, Stefan, I'm pretty sure you got it. Okay. Anybody? Can you tell me what's wrong, or you think that's going to work? Basically, I have no if then else. Exactly. That's exactly right. Okay, you can answer the second one. Okay. So basically, you're exactly right. This is a very typical mistake where you don't have base case. Think about base case. Whenever you say missing base cases, that means no termination. Base cases are the situation where you try to stop making any further recursive call. Well, what's going to happen is like this. If I want to calculate factorial 3, what's going to happen is factorial 3, in turn, is going to be factorial 2. In turn, it's going to be factorial 1. In turn, it's going to be factorial 0. Do we have a base case to stop it? No. Factorial minus 1, factorial minus 2, etc. If you try this in your computer, I do encourage you to try just once. You'll find that your computer will just get slower and slower, and also getting louder and louder, because you got infinite loop. Okay? It's very common. Are you comfortable with this? Okay, no base case. Always put base cases, always. Again, base cases are the situation where the problem can be solved right away. Second version, I do have base case. I do. I say, if n is equal to 0, 0 factorial should be 1. Do you see any difference here? At least notice the difference, right? Okay, you want to try? Yes. Are you complaining about the if part or the else part? Just tell me which part you don't think that's okay. The if part, I can tell you, seems okay because we say if n is equal to 0, that means we can solve the problem right away and then just give you 1, right? Just return 1. Okay, let me see it, otherwise I'll point to you. Anybody else want to try? Yes. Aha, exactly. So this is another common source of error. Remember I said every time you want to make a recursive call, you assume you got some solution. However, the solution must be to a strictly smaller problem, okay? Think about what you're trying to say. I'm trying to solve factorial of n. The way I solve it is to say now n times the solution to the very original problem. That goes into infinite loop. What's going to happen is if I got factorial 3, first of all, it's going to be activated, and then when I make a recursive call, it's going to try factorial 3, and then it try factorial 3, and then it try factorial 3. It goes like that. Okay, you still got infinite recursion. You still, well, the idea is you still have no chance to reach the base case. Okay? Yes? Definitely, you just get infinite loop. You can think about this. The way I show the infinite recursion is to show that the size of the stack can keep growing until you run out of memory.
So would it eventually result in a stack?
It's like a stack overflow, yes. Yeah, but that conceptually is like an infinite recursion, conceptually, yes. Mm-hmm. So anytime you see stack overflow, exception in Java, that's pretty bad. That means your code will never terminate, right? All right. So these are the two common mistakes you want to avoid. Always have a base case, and always when you try to make a recursive call, make the call on a strictly smaller problem. Okay? Let me give you a little bit preview. In this case, we are just passing an integer to the factorial. So the way to make the problem smaller is by saying n minus 1, for example. Right? We're going to see lots of examples about doing recursion on an array or on a list. Conceptually, intuitively, if I give you a list of size 10, what can be a smaller problem of size 9 or half the size, right? That's something we'll see, how to make a recursive call. But we'll give you intuition. We'll get there. Okay, that's about factorial. And then what I would like to do now, okay, exactly what I just illustrated. You can also see the stack trace over here. And then, so that's more detailed explanation. You can look at that. Everything has been covered. That one just talk about factorial 5 rather than just 3. Okay, what I would like to do is talk about Fibonacci number. Okay, for those of you, just in case you haven't seen Fibonacci sequence, I want to be fair. So I just want to show you very quickly what a Fibonacci number is. It's a sequence. You say 1 and 1. So this is Fibonacci of 1. This is Fibonacci of 2. 1 and 2 is always 1. And then, starting from Fibonacci of 3, you always try to calculate this based on the 2 previous numbers. In this case, 1 plus 1, 2. How do you calculate Fibonacci 4? It will just be Fibonacci of 3 plus Fibonacci of 2. In this case, 3 and 2. You got 2 and 1. So 2 plus 1, you got 3. Okay, quick check. What should be Fibonacci of 5? 5, right? Add these up together. I'm not sure if you realize the way I explained this problem here, I already gave you hints about how you can define this solution here recursively already. Yes, but it's okay, yeah. Solution, not yet, okay. Actually, I would say Fibonacci problem itself is very naturally recursive, but we'll see. Okay, actually this is already recursion, so let's let you answer another one. Okay, that's the definition here. You can see, are you convinced this definition here is recursive? Let's see why, okay, just in case you're not so sure. If I go back to the iPad over here, okay, so now you can think about n over here is the size of the original problem. Original problem. You can think about this guy over here is the solution to a strictly smaller problem. Why is it strictly smaller? Because n minus 1 is strictly smaller than n. Okay? And then this is just the solution to another strictly smaller problem. Another strictly smaller problem. However, having f n minus 1 and f n minus 2, each one of them in isolation is not a solution to the final problem. So the combination is really important. Again, let me emphasize. Remember the pattern over here? We said you should always try to combine. Combination is really important. Okay? Okay, let me just go back. Okay, so now how do we combine them? You simply use plus. So that's why you will see over here plus. Okay? So this is to combine the solution together. Okay, any questions about this? Okay, let's try to see how we can define the code, which is also easy, and then we'll try to trace the code very quickly. Okay? That'll be the final time we use the stack. Let's say we define a method over here called Fib, standing for Fibonacci. And n over here, we say if you, again, think about what are the base cases. In this case, these are the two base cases, because for them, you know you should be 1 right away. You don't need to have any further consideration. If n is equal to 1, result should be 1. If n is equal to 2, result should be 1. Okay? And now this is where the recursion happened. And what's so interesting about this example here is, in the previous one about factorial, we are making just a single factorial call, right? N times factorial of n minus 1. But now we are making 2 recursive calls. That's why tracing it would be worth doing. Fibonacci of n minus 1, which is strictly smaller than n. Fibonacci of n minus 2, which is also strictly smaller than n. Okay? Are you okay with the code, first of all? Okay? Somehow you can see for Fibonacci n minus 1, Fibonacci n minus 2, you don't try to solve them implicitly. Somehow it will just work out. It will. Okay? But let's see why. Okay? Let's do a small enough example. We want to do Fibonacci 4. Okay? Before I get to it, I want to give you a little bit preview of what's going to happen. If I want to do Fibonacci 4 over here, I know that 4 is too large for me to solve. What I will do is, it will be split into n minus 1 and n minus 2, right? It will be split into two things, Fib 3 and Fib 2. We go from left to right, okay? So this should be done first. Is Fibonacci 3 too big? It is. Split further. That'll be Fib 2 and Fib 1. And then, is this small enough? It is. 1. It is small enough. 1. And then you say plus. That's how you combine. 1 plus 1 will give you 2. And then we go to this right-hand side. What's Fib 2? Just 1. Okay? And then combine them together. 2 plus 1 will give you 3. Okay? That's why this guy should be 3. Okay? Guys, are you okay? All right. Let's trace it very quickly. Okay? That's the big picture. That's exactly what you will see me doing. Okay, let me just say one more thing. One thing to note. You will actually see the following when I do the stack trace. This particular guy over here tell you about what's Fibonacci 3. This guy will be done first before we even start with this guy, because this guy appear at the left and then the right. Okay, let's see. Let's now try to trace it. Okay. Okay. So now let's say we try to do Fibonacci of 4. Okay, push that onto the stack first. Fibonacci of 4. And then we know that it's not the base case, so we'll actually reach this line here. Okay, just to tell you that. So what we will get is, it's going to be Fibonacci. Let me make the pen a little bit thinner. It's going to be Fibonacci of 4 minus 1, 3, and plus Fibonacci of 2. Okay. Conceptually. But now, it's addition. We cannot evaluate the right-hand side until we know about the left-hand side. That's the rule, from left to right, like a short circuit, basically. So now what we will do is, we'll try to do Fibonacci 3 first. So we push that onto the stack, Fibonacci 3. Fibonacci 2 is not underlined, so that's still suspended, okay? So now, Fibonacci 3 is now active. So now what we'll do is we're going to do Fibonacci 3. And now, that's not the base case, agree? So what we will do is we're going to say execute this particular recursive case. What we will get is we're going to have Fibonacci of 2, right? 3 minus 1 will be 2. 2 plus Fibonacci of 1. Okay? So now what should we do? What we should do is we're going to execute this guy here first from left to right. So that's a left guy. Okay? So now we're going to push Fibonacci 2 onto the stack. Okay? So now Fibonacci 2 is now going to reach the base case. And now it's going to tell us it's simply just going to be 1. Agree? That's going to give us 1 over here, and then it's done. Question for you. What should we do next? Fibonacci 1, yeah, that's the right-hand side, right? You actually want to do from left to right, okay? So now after this guy here, what you would do is, after you have done with the left-hand side, it's now actually going to be 1 over here, Fibonacci 2, we just returned. And then what you will try to calculate is this guy over here. So we're going to put Fibonacci 1 over there. Let me use a different color. Maybe orange is fine. Fibonacci 1, push that onto the stack, and now, are we reaching the base case? We are, right? 1 is base case. So we're going to reach this particular base case, and then it's going to tell us it's simply 1. So that will also give us 1. So that means this guy here is 1. 1 plus 1 will give us 2, okay? So that's basically, we are going to finish the a result for Fibonacci 3, right? Because after that, it's now going to be done. Okay, sorry, that should be pop off. And this should be 1 plus 1, that'll be 2. Okay, so far so good. Now, what's to be done finally? Okay, let me speed up a little bit. Okay, that's kind of the tracing that's going to happen in your computer. Okay, after this, we know that Fibonacci 3 is going to return back to us 2. So that means this guy here is going to give us 2. We are done with the left-hand side. We should now do the right-hand side. For the right-hand side, it's going to be Fibonacci 2, right? And that means we have to push that onto the stack one more time, okay? And now this will be Fibonacci 2. And we agree with that. It's base case, right? So that one is simply just going to return 1. I'm just safe one tracing for you. So that's going to be 1. And then you got 2, you got 1. So now you know that eventually 2 plus 1 is going to be the result for Fibonacci of 4. So it's going to give you 3. You can see tracing this kind of stack is quite tedious, right? Also very easy to make errors. But I do want to show you just one time. You know, that's kind of how things are going to be executed. However, I would say in general, if you want to solve the problems that we give to you in the lab or the test or the exam, that's not the way to think. But I'm going to do it just once for you, just over here. Any concern about this? If you really want to do practice, try Fibonacci 5. If you want to try, do it on the paper and show me your answer. I'll go over with you. Okay? That's an optional exercise. Okay? But now I'm going to assume you have some basic knowledge about tracing them. Okay? But for all the later, more complicated problem, we're going to use the higher level way of tracing it. Otherwise, it will take forever to teach you this. Okay? Good. If you have no question about Fibonacci here, let's do some more interesting problem. Okay? These are the two typical ones we talk about before we talk about some interesting problem. Oh, by the way, that's actually about Fibonacci 5. Okay? If you want to go over that, feel free. No problem. Okay? I'm not going to save you some time. Okay. The first one, we're going to solve hopefully about 3 to 4 or up to 5 problems today. Okay, from now on. For every problem there, I will give you some intuition, and then I'll help you come up with a solution. The code itself is quite easy to write once you get the idea straight. Before I do the first one, I want to make sure you're comfortable with certain methods in the string class. Okay, let's do that quickly. Okay, in the string class, okay, so now let's say this. We have a string S, A, B, C, D. Okay, you can think of it as an array of character. You can think of it. So you got A, you got B, you got C, you got D. Okay? And now I want to talk about a method called substring. Okay? For those of you who haven't used the substring, I want to highlight to you the tricky part about using this method here. Conceptually, it's saying that you want to take a part of the string as a new string. The way you take it is by specifying some lower bound of the index and some upper bound of the index. Okay? I want to make sure, are you comfortable with this closed interval and open interval notation from your math? Okay? In case you're not, okay? This simply means it's inclusive. This simply means it's exclusive. So what's happening here is, when I say, let me just give you another example. If I say 0 and 4, I'm not trying to say get the character 0, get character 1, character 2, character 3, and character 4. No. Only up to, but excluding the character at position 4. That's the tricky bit. Okay? Let's try. So now, if I try to do this guy here, the first one. If I say substring 0, 0, what am I going to get? Take a guess. Am I going to get just A? Or am I going to get nothing? The answer is nothing. Because thinking this way. You can think about, when I say 0, 0, I'm saying, give me the character from 0 until this upper index minus 1. Would that be a valid interval here? Not really, just empty. Okay, so this will just give you empty. That's kind of the base case, well, like a simple case. How about this guy here? If I say 0 to 4, which one is it going to give to me? Is it going to give me A, B, C, D? Or A, B, C? A, B, C, D, right? Think about what's happening here. You can do some little bit manual translation. What this tells you to get from the string S0 until S3. That's what it is saying. Okay, so 4 minus 1. So in that case, it's going to give you basically the entire string over here. Okay? And then one more thing. One more. How about this guy here? What about from 1 to 3? What would that give to me? I heard BC. Anybody else? To help you a little bit, why don't I annotate the indices? 0, 1, 2, 3. If I say 1, 3 over here, that means get from S at position 0 until S at position 2. Right? So what I would get is basically ABC. Let me just show you one more thing to get your understanding straight. Oh, yes, yes, absolutely. You guys are really listening. I appreciate that. B and C. 1 to 2, right? I should really say the following. Again, my apologies. What I meant to write over here is S1. That's what I meant to write. Okay. Let me reinforce your understanding one more time. Can you tell me the following? Given any string S, any string, what's going to be the following expression? S dot substring 0 S dot length minus 1 plus S dot, oh, sorry about that. Okay, let me write it again. Let's say I, where, let's say I is a valid index. Okay, any I, as long as it's valid. Substring I here, and then I would say S dot length. That's where I meant to put it. What's that going to be? Any string, any I, as long as it's a valid index into the string. Okay, I'll take you for next one. Yes? Correct? I agree with you. The first one going from indices 0 to I minus 1. Yes. The second one going from I until s dot length minus 1, basically the last index of the string. What will be the concatenation of that? Yeah, just get back to s. So it's more like an algebraic property. Right? I'll give you one example. Okay. Well, just to emphasize to you, so that will just, equal, I mean mathematical equality, right? I don't mean the reference equality. Okay, it just be s. Okay. One example quickly. Let's say here we got 0, 1, 2, 3, and then we got A, we got B, we got C, we got D. Let's say this is S. If I say S dot substring, I say from 0 to 2 plus S dot substring from 2 to S dot length over here. Okay, let's do some little bit substitution very quickly. S dot length, what would that be? 4, agree? Okay, 4 characters. So that would be just 4. So 4 would not be inclusive, right? It would be exclusive. So now, let's think about what's going to happen here. S dot substring 02, it will contain how many characters? 2 characters, right? A and B, okay? What about S dot substring from 2 until 4 exclusively? Well, basically from 2 here until 3, basically CD. Concatenated them together, you got original string. Okay, just one example. Okay, substring is your friend for the problem we are trying to solve. Any question about substring? Okay? If you're okay with it, let's solve it. Solve a problem. Palindrome. Do you know what a palindrome is? Okay, let me review. For those of you who don't know, okay, it's for your information. A palindrome is simply a word that if you read it forward and backwards, you read the same. For example, is empty string a palindrome? Yeah, if you try to read an empty string forward and backwards, just empty string, yes. What about A, a single character string? Yes, A and A, right? What about madam? Okay. What about race car? Yeah, okay, good, yeah, the same, right? What about man? No, okay. Any question about the problem itself? Palindrome. If you want to solve this using a loop, that will be interesting exercise anyway, but that's not our concern. Is it possible to solve the palindrome problem recursively? Basically, you want to think about if I'm given a string of certain size, if the string is too big, how can I assume a solution to a strictly smaller problem? Meaning that if I can somehow know a substring of the original string, if I know if the substring is a palindrome itself, can I somehow combine that answer with something else and get the original solution? Is it possible? I'll give you about 30 seconds to think about it, and I'll give you some visual hints. Okay? The code itself is trivial once you know the idea. So that's why I want to spend more time on the idea. Okay? Okay, think about it for 30 seconds. Okay? Okay, I'll leave that to you over here. Let's take a race car as an example. Let's say I give you this string with so many characters. You don't necessarily know what the answer is right away. I want to somehow break it down into smaller problem or problems, doesn't matter. In general, it can be several problems, okay? However, the solution to the sub-problems is going to help me on solving the original problem. That's the key, okay? Let me give you a little bit hints to lead you to the solution, okay? Since I talk about breaking down the string, there are many ways I can break down the string. For example, I might break down the string this way. If I can tell you whether this string is a palindrome or not, and then you're left with just a single character, do you think that will help you? That's one way to think about it. Or if I try to break down the string to this, the tail, and also this guy here, if I know whether or not this is a palindrome or not, and then I only left with this character, can I know if that's a palindrome or not, right? That's kind of the problem you want to think about. Okay, so now let me tell you possible answer. Anybody want to suggest your solution? Tell me what a strictly smaller problem might be useful for solving this.
You can use 0 to s dot length minus s dot length minus 1 to get off the very first character, and then you can do s dot length minus 1 to s dot length to get the other very first character, and then compare those, and then just move it smaller and smaller.
So you're basically talking about you're trying to define a strictly smaller problem to be the middle part without the first and the last character.
Yes.
Am I right? Okay, that sounds reasonable. I'll show you what that is. Yeah. Don't feel too bad if you cannot come up with the answer right away. That's okay, right? You need some practice. What you're suggesting was the following. If somehow I can delegate this strictly smaller problem to my to recursion, all I have to make sure is, in order to be a palindrome, this guy here must be the same guy as this guy here, right? If I simply got R and A, is it possible for that to be palindrome? No way, right? So now, if I know that R and R are simply the same, I have a chance. And then I ask the recursion whether this particular substring is a palindrome or not. Okay? In order to solve it, it is still too big. So what I will do is I'm going to break it down into a smaller one in the middle. And then I ask the recursion, is this guy here a palindrome? And then at the same time, A and A, are they the same? They are. Okay, so now, is this a palindrome? Is it immediately solvable? May not be, right? It's still a little bit too large. In that case, I can break it down further to say, I can now break it down into just the middle part. Just get rid of the beginning and the end. Okay, so the beginning and the end is actually C over here, and then just compare them. That's kind of the idea. Okay, so the main lesson to learn from this example is one way to make your array of character or string smaller is by taking just the middle, by discarding the beginning and the end. Okay? Let's now have a look at the code, and then I'll show you how you might trace it quickly. Okay? The code itself is quite intuitive, okay? But I'll help you with that. Basically, you're going to first of all talk about base cases. I'm simply saying if the length of the word is 0 or 1, okay? Because empty string is palindrome right away. Or if I got a single character string, that's also palindrome, no problem. Okay, I would just say return true. That's a base case. What about recursive case? Recursive case would be, in general, if I'm given a string like this, okay, that's a string, starting with index 0 all the way to string.length minus 1, okay? And now I simply get to say this is the first character. And this guy over here is the last character. And then whatever that's in the middle, I'm going to use a substring method to calculate it, right? So that's why you see the substring. That's why I talk about substring first. That's the middle. So now, whether the whole thing is a palindrome or not depends on the combination of things. The first character must be the same as the last character. And also, the middle part must be a palindrome. And now, one thing to notice. Middle versus word. Are they the same problem to solve? They are not. Because if you look at what's happening over here, if you look at the diagram over here, you can think about this whole thing over here is the word, including the first and last character. And now when we talk about the middle, it's actually this middle guy over here. So this is the middle. Okay, so middle is strictly smaller than the word, conceptually. So that's why you can use recursion to solve it. Okay, that's palindrome. Let me trace that very quickly together with you. Okay, let's choose 2 examples. Okay, let's see the first one. Let's say is palindrome madam. If you allow me, I just wouldn't put the quotes just to save it, save some writing. In order for me to solve this, I have to, first of all, see there's a first character, last character, and then this is the middle part. So this can be broken down into 3 parts, 2 parts basically. First character is m equals m, and that's how we combine. And then it would say is palindrome, and then ADA. That's a substring. Are you okay with that first call? Okay, let's go a little bit further. And now, if I want to deal with this guy here, too big, first and second character, okay? Break it down into two parts. A equals A, and also this is the middle part. Is palindrome of D, okay? Finally, is this small enough for me to solve? It is, right? Size 1. So this will just give me true. Oh, and don't forget, we are trying to combine them using conjunction, right? So now, eventually, what it will be calculated is A equals A, which is true. M equals M is also true. So true and true and true. Eventually, you get true. That's how you trace it. Let's do one more, okay? Just to see how you might return false. I'll just make it up. Let's say A, B, C, A. Okay? I want to know whether there's a palindrome or not. In order to tell, too big, first and second character. And break it down. That's the middle. So that's going to be break into A equals A, and then is palindrome BC. However, this is still too big, right? It's not size 1 or 0. In that case, first and second character. B equals C, and then is palindrome now, what will be the middle part? Empty string, okay? In this case, because once you take the first and last, you just got nothing left, okay? Just something you can double check. So it's palindrome and the empty string. We know that this guy here is going to give us true. However, this guy, false. This guy, true. True, oh, of course, I forgot to write it down. For every level, you try to combine them using conjunction, right? True and true, false, right? You got at least one false. That's palindrome. Any questions about this palindrome? For your lab number 5, now lab number 4, hopefully lab number 4 will be released soon, okay? Lab number 4 will be about collection. Lab number 5, I will give you some exercises on recursion, okay? Maybe we can talk some of them in the class to emphasize your understanding, okay? Yes, question?
When B is not equal to C, it won't do the...
Oh, you talk about short circuit. Yes. What you're concerned about is short circuit, yes. But now just to really trace completely, I'm just saying conceptually you can think about, since you got false, at least one. But maybe when they evaluate, as soon as they realize this is false, they wouldn't continue, yes. Yeah. But it wouldn't hurt to think that way either. Okay, good. Okay, let's do a more interesting one, okay? Okay, we're getting more and more interesting. Palindrome, okay. How do you reverse a string? Okay, basically, you want to, given a string, you want to return its reverse. Basically, given a string, return a string. Okay, let me give you some example. What will be the reverse of empty string? Basically, base case, empty string. Okay, reverse of just a single character string, the same string. Okay, what about AB? BA. Okay, what about ABC? CBA. ABCD, DCBA, okay? Conceptually, it's easy to describe the problem. Now, how can we solve it recursively? Again, think about how you might approach the problem. Think about if you can assume you have the solution to a strictly smaller string where you know about its reverse. Is it possible to apply that solution there of the reverse of some strictly smaller string and combine that with the rest of the string and get a reverse of the original problem? Think about it for 30 seconds, and then I'll give you visual hints. Think about how you might break down the string. Should you break it down in the same way as we did for palindrome, to take the middle part? Or should we break it down from the front? Should we break it down from the end? I don't know. Okay. You might think recursion is very weird, right? But I think that once you really click on the recursion idea, it's actually a more natural way of thinking than loop. Yeah. Hopefully by the time you graduate, you can appreciate that. Doesn't have to be now. Yeah. Got a question? Yeah.
Recursive is like
Oh, good question. Is recursion a better way, is better thing to have than loop? No. I would say recursion and loop, they are almost equally, they are equally powerful. However, there are certain problems which is easier to think about recursively. There are also certain problems that's easy to think about iteratively. I would say once you get more experience, you can judge. I would say for me, when I write a code, sometimes I find it easier to write a loop. Sometimes I find it easier to write recursion. I think it depends. Yeah. I think you will have more understanding about recursion once you go to 2011, 3101, the more advanced course. Yeah. You got some questions or thoughts? Sure. Let me just, sure. Okay, if everybody's ready, let's hear. One moment. Let me open a new page. You want to describe the idea first?
So in the method, just return the last character plus a recursive code with a substring up to the last character. So not including the last character.
Okay, you're saying that, okay, you're breaking down the string to two parts. Second part is just the last character. And the first part is nothing but the last character, everything but the last character. And somehow do something about it. Yes, I see what you mean. Okay, that's pretty good. Okay. Okay, guys, actually, he's pretty good. He actually got the right track, at least similar to my solution, or the same. I'll start right away with that. I'll give you some visual summary of what you said. Okay. Let's say we are trying to calculate the reverse of ABCD. I hope you understand the solution. That's my intention. We know that this is input. The output that we expect is D, C, B, A. And I want you to make the following observation, okay? And I'm not going to say anything, but hopefully you can see from the color annotation. Actually, can you see what I'm trying to do here? Somehow the green in the input is the first character. Somehow it becomes the last character in the reverse. What about the pink? The pink part are not exactly identical. BCD and DCB, they are not equal. So you cannot simply swap the both, right? What's the connection between the two pink? The reverse of each other. That's exactly why you can use recursion, right? So what we can learn from this particular example over here is as follows. In order for me to get a reverse of this particular string, I will break it down into two parts. The first character and everything else. And then this is how I'm going to combine the result in the final string. I'm going to put the first character at the end as the last character as the output. And then for this guy here, it represents a strictly smaller problem for me to solve. In which case, I'll simply say the reverse of, for example, let's say reverse of B, C, and D. In that case, that will give me D, C, and B. Okay? Conceptually, that's how you can think of it. Okay? Let's have a look at, let's do some trace very quickly, and then we can look at the code. Okay? The code is very similar to what I'm just saying here. So now, let's see this. Let's say, let me just make sure the method name I want to present. Okay? Reverse of. Okay, let me just stick with that. Let's say I want to calculate the reverse of let's say, how about EFGH? Doesn't matter. Okay? Let's say that's what I want to calculate. Oh, again, let me just get rid of the quotes just for simplicity. Okay? So now, in order for me to do that, I need to break it down into two parts. I'm going to say this is the first character, and that's the remaining part. So this can be broken down into two parts. E will now be the last one, concatenated with the reverse of F, G, and H. Okay? I'm okay with the first step here. And then this is too big. So what I will do is first character here and the remaining part. So break it down into first character now become the last character, concatenated with the reverse of GH. Okay, so now finally, we're not in the base case yet. So what I would do is I say green. And then first part, and then the remaining part. So what I will do is, it's going to be G has now become the last character. And the remaining part is simply reverse of H. Do we have to go any further for recursion here? We don't, because single character, that's the base case, right? So now in this case, what you will get is have some return from the stack. So this guy over here is going to give us H. H plus G plus F plus E. That's the final answer. Any questions? I hope I'm not going too fast. Okay? But I think a recursion, all I'm asking you from the lecture would be get some general idea to see. I keep emphasizing smaller problems and also combination. That's the key. And once you struggle a little bit with the lab number 5, you can talk to me again. Right? You need some practice. Okay, if you don't mind, I'm going to go for the next one. Let's see what the next one is. Reverse of string over here. Okay, this one is also interesting. Number of occurrences. We want to count how many times a particular character occurs in a single string. Okay, let's see. What we will see is this. Let's say, okay, let's try to understand what's going on here. Let's say we are defining this method called occurrencesOf. How many times does character A appear in the empty string? 0 times, right? It doesn't appear at all. How many times does A appear in A? 1 time, okay? And now, how many times does A appear in B? 0, right? How many times does A appear in Baba over here? Can you see this 3 times, right? First time here, okay, basically index 1, index 2, and also index 4. Okay, 3 times. Okay, one more. How many times here? B? 2 times. Okay, that's about a question. How can you solve it recursively? Similar idea, right? You can see, so hopefully you can get a little bit like intuition. Somehow you want to break the original problem, the string, into several parts, maybe 2 parts. And then maybe for the first part, it's trivial to compare. For the second part, you have to rely on recursion. Okay? Again, I'll give you 30 seconds to struggle a little bit, and then we'll talk about the solution. Okay? For this one here, I'm going to explain just the general idea, and I'll leave the code to you. Okay? What I will do is I'll try to use one of them to explain. Okay? I'll use this example here. Anybody? Okay, Stefan, please.
So I would think we'd have 2 base cases.
2 base cases? Sure.
General.
Sure.
So one when it's an empty string.
If you got empty string, then you always return.
0.
I agree. Everybody agree? Okay. Empty string, nothing can appear. Okay. Yes, second base case.
And the second case is just 1 letter.
Sure.
So the first one, get the first letter.
Mm-hmm.
And so we have a counter, for example, initialize a counter. And if that first letter is equal to the first letter, then say 1, and then call it recursively for every other substring that's going from left to right.
Mm-hmm.
And then if they're all true, all add up to 1 plus 1.
Yeah, when you say if they're all true, add up to 1, somehow you're thinking a little bit too low level already. You're thinking about all the recursive call. How about I help you a little bit? Stefan is getting very close, okay? Let me help you a bit over here. Let's say I got this particular string here. Let's say BA, BA, okay? I want to know how many times character A occurred inside, okay? If I can somehow, I'll just follow your logic. I compare A with B, the first character. Are they equal? They are not. So that means that alone, just 0, okay? And then I consider the remaining part of the string and ask the recursion, how many times does A occur in this particular strictly smaller string? In that case, it will be 3 times. recursively, right? So that means eventually my answer would just be 0 from here and 3 from here, 0 plus 3. Okay, let me trace it for you. Okay, you will see. Okay, that's exactly right, but you just somehow want to organize your thoughts a little bit. Okay, let's try this. So now the way to break it down is very similar to how you do the reverse of string. Okay, so what I will do is I'm simply going to say first character over here and the remaining part of the string. Okay, so what I will do is, so now I know that A equals B is not the case, right? So that means in that case, that should be just 0. It should be added up to a recursive call. So that should be the occurrence of AABA. You can see there's a substring over here, AABA, and then A. Okay, that's the first step. We are not done yet because we don't know yet what the recursive call is going to return. So we're going to go further. Okay, let's go further here. And then we say, again, we consider just the first character here and then break it down into 2 parts. Okay, and then we say A equals A. So now this time, this occurrence should count. I'm going to put 1 here. Plus a recursive call to the remaining part of the string, which is A, B, and A, and then A. Okay? And then this is still too big for me to calculate. So what I will do is I'll try to do a little bit more. So this is the first character, and that's the remaining part of the string. And then you break it down into, so now A equals A will give 1. Every time if the single character is equal, that's just, sorry, I thought I made a mistake. Okay, good. So A equals A here, right? So that would be 1. And then we're going to say occurrences of, again, a strictly smaller problem, BA, and then A. We're getting there, okay? And then we are not done yet because BA is still too large for us. We can only consider maybe the one single character to be small enough. So B here, and then the remaining part is simply just A. So we'll say B equals A, which is false, so that will be counted as 0. And then the remaining part will just be occurrences of A and then A. So now this is kind of the base case. It's a single character. If there's only a single character, you simply compare that with the character. True, so that should be counted as 1. Okay, don't forget you also got plus over here. Okay, write a plus. Okay, plus, and then, so this one, A equals A, that's true, so we get 1. So now if you add it up, 1 plus 0, let me use a different color here. So 1 plus 0 plus 1 plus 1 plus 0. Okay, 3. That's the final answer. Okay, conceptually, that's how you can think of it. You break down the string into 2 parts. The first one, the first character, and the remaining substring. And then every time, if the first character you extracted currently is equal to the character A you want to match, then it's counted as 1. Otherwise, it's 0. And then let the recursion handle the rest. Yes?
I think for a problem like this, an iterative approach would be much simpler.
I agree with you. Actually, you might be having the same concern as Stefan has. Maybe solving this problem iteratively using a loop would be much easier. I wouldn't say that's wrong. If you have no constraint, which either use a loop or use a recursion, absolutely you can use a loop if you wish. However, since now we want you to practice recursive thinking, that's why I'm doing this way. Yeah, that's no problem, absolutely. So I would say in the test or in the exam, if we don't tell you whether you should solve a problem iteratively or recursively, use either way you feel comfortable. But if we say you gotta solve it recursively, sorry, you gotta use recursion, okay? But it's good for you, recursion. You definitely will like it later. Okay, the only thing I want to highlight in the code is this. Okay, over here you can see reverseOf over here. Oh, sorry about that. reverseOf, and then you can see base case either it is empty, return empty string. Okay. Oh, sorry, not reverseOf. What am I doing? I'm way behind. OccurrencesOf. Sorry. OccurrencesOf. If it is simply just empty string, as you said, it always returns 0. Otherwise, it's non-empty string. You first of all get the first character called the head, and then you get a remaining string called the tail, exactly how we broke down the string. If head is equal to the character we are looking for, in that case you count as 1. Otherwise, you count it as 0. And then you're making 2 independent recursive call to figure out the answer, right? You can see these two recursive calls are exactly the same. And now, let's do some healthiness check. We said there should be two common errors you should really avoid for recursion. Do we have a base case here? We do, so that's okay. So now, every time we're trying to make a recursive call, are we trying to pass a strictly smaller input? We are, okay? Let's convince you. Because if you look at the tail over here and the tail over here, they are strictly smaller because it's a substring, right? Okay, that's about the occurrences of, okay? What I want to do, we got about 10 minutes-ish. Number of occurrences. Now, I want to talk a little bit about making recursive call on an array, okay? I can only give you a little bit idea about the general solution. I'll mention that in 10 minutes, and then on Thursday, oh, not Thursday, today is Thursday, right? Tuesday, after the weekend. We'll spend about maybe 10 or 15 minutes talk about one or two examples on the array, and then you'll be ready for the lab, okay, for the recursion lab. And then we're going to go to another topic, but we're going to revisit recursion towards the end of the semester, okay? Let's just do something very quickly so you can think about it over the weekend. Now, think about what we want to do. Before I go over this particular solution strategy here, that's what I want to do in the next 10 minutes. Before that, I want you to think about how we can solve this problem here recursively. Let's say you're given an array of integers. I want you to solve recursively. Are all the integers in the array positive? Okay? You can think about, actually, since you have got the intuition from the string and also the string, also the number, you want to think about how can I make this problem smaller? If I can somehow only consider the first number in the array to begin with, and then the rest of the array like a subarray, strictly small array, but somehow, how do I pass this subarray as arguments? How do I do that? You see what I mean? That's exactly what I'm going to talk about now. Let's say this. Let me give you the intuition here. Let's say this is the array you're given, 0, 1, all the way to a the length minus 1, a. The question is, are all the numbers in the array positive? Conceptually, I first of all consider if the first element over here is positive. And then recursively, I'm going to consider whether all the elements in the subarray, except for the first one, are all the numbers positive. If the orange part gives me true, and also the pink one is positive, combine them together, it should be all positive. You see what I mean? Okay. Now, here's a question for you. If I want to make a recursive call on a strictly smaller array, how am I supposed to pass that subarray? How am I supposed to? Your first response might be, which I would like, is to, you want to say something first? Yes, go ahead. I like that solution because it's bad, okay? Sorry, I don't mean to embarrass you, because that's, I would have thought about that way myself. What you're saying is, in order for me to create an orange array over there, you will simply maybe run a loop going from index 1 until the last index, create an array. Now, let's say the array size is 1 million, let's say. How many times do you have to create a subarrays? Maybe about close to 1 million. That would be quite a waste of memory, okay? So that's why we want to do something a little more efficient. However, we are trading complexity for efficiency. We're going to have something that's more efficient but slightly more complicated. Naively, you can just create a subarray, completely new one in the orange part, for the orange part. But that's not so good. Stephen, want to say something?
What if we, I'm pretty sure this is not right, but what if we just use like a remove entry kind of method that we used before?
You're saying remove entry, but remember, if you want to remove entry, somehow you want to shift everything to the left, or creating some null slots. That will also create complexity for your stuff over here, okay? So now, let me give you a little bit intuition, okay? The intuition is, think about indices before I get to the code. Let's say this is I'll make it even more concrete for you. A, 0, 1, 2, 3, 4, and 5, okay? Now, let's say this. If I actually want to have, let's say, only the first elements over here, that's the first, oh, let me be consistent with the color. That's the first elements, and then this is the remaining part of the array. Pink and orange, right? Now, rather than creating a new array aside, completely new, I don't want to do that. What I can say is, I'm going to pass call by value. I simply give you the address of the array. The same array, I don't create any new one. However, what I will give to you is which index interval to look at, right? Now, the entire array will be from 0 to 5. If I want to look at a subarray, I will tell you now, look at from 1 to 5. Maybe the next recursive call, look from 2 to 5. And the next one from 3 to 5. And then 4 to 5. As soon as you get to 5 to 5, in this case, you know you're looking at a single element. You're reaching the base case. So now the complication we're adding here is as follows. Rather than considering the entire array, we are considering the indices you want to look into. Okay, that's the idea. Okay, let me go over a little bit with the code with you conceptually. Think about it over the weekend, and then we'll talk about it. Just give me 2 minutes, and then I'll let you go earlier today. Okay. Okay, so now if you look at the code in your slides, okay, I'm going to go over these guys next time, but I just want to highlight to you. So there is a single slide. I'll do the example next time. What I want you to pay attention to are the following. Okay, you can see this is M, and we are trying to make a recursive call. This is subarray. The naive solution will simply do what you initially suggested. You will simply just create a new array over here, and then we say that it might work, but it's very inefficient. Just create a new array. Okay, that's the no. We don't want to do that, okay? What's the final solution? Now we're going to say, in order to solve this particular M recursively, we're going to pass also indices over here, okay? Just notice that we are saying some index over here and some index over here. Every time you want to make a recursive call, you want to make sure, basically, if you look at the example I did for you, this is the from. The first time is 2, and then 3, and then 4, and then 5, getting closer and closer to the end. That's kind of the thing we want to do, okay? So that's kind of the recursive call you will see. That's all I want you to briefly look at before Monday. So next Monday, we're going to review this, do a very quick demo, and then we'll talk about 1 or 2 examples, and then we'll move on to another topic. Okay, I'll see you next week.